In this video, I'd like to cover 3 examples of balancing chemical equations, except these are 3 examples that are special cases of balancing chemical equations. What I mean by special cases is that you do not have to use these hints and methods that I'm going to show you, but it will make it so much easier when balancing these types of chemical reactions. So I'm going to call this special cases of balancing chemical equations. So special cases of balancing chemical equations. The first one, if water, H2O, is on the reactant side and the polyatomic ion OH is on the product side, change H2O into HOH. So this will be a hint in solving chemical equations when H2O is on the product side of the equation. The problem that I'm going to do for you is this. It's going to be Ca, the metal Ca, reacting with H2O, turning into CaOH2 plus H2. If we were to solve this equation just our regular way, atom inventory and do all of that, it would be fine, but in many cases it would be very difficult to solve without doing this hint. So the hint is we're going to change this whole thing, H2O, which are 2 H's and 1 O, we're going to rewrite it as HOH. And when we solve, because HOH is still 2 H's and 1 O, it's just written differently. So we're going to kind of shade that out, get rid of it, and rewrite it as HOH. So now when I do my atom inventory, when I complete my atom inventory, I have Ca, and I'm going to keep this group of OHs together. And so instead of counting those O's and H's separately, we're going to count them together as a group. So what we're going to do when we list our atom inventory, we're going to list Ca, we're going to list H, and we're going to list the group of atoms OH together. And we're going to count them together. Now, right now, it will probably seem like, man, this is a lot of work and more complicated than just counting the individual atoms. But it turns out in many cases, this is really makes it easier to solve the equation. So notice there's H individual, but there's also a group of OH. So when we count, we get 1 Ca, 1 H, and 1 OH on the reactant side. Over here, we get 1 Ca, we get 2 individual H's, but look, there's a 2 on the outside of this, so we get also 2 OH's. So in my mind, to solve this, I want to be able to cross out the 1 and put a 2. To be able to do that, I'm going to put a 2 right in front here, and that will give me 2 H's. So I cross this out and put a 2. But it also gives me 2 OH's, and that's all I need to do to solve the problem. I will tell you, this one looks fairly simple, and you might be thinking, wow, we did a lot of work to be able to just solve that. I could have solved it easier without using this trick of changing the OH into an changing the H2O into an OH. But I will tell you later, it'll be a much different process, and it'll be easier if you do this trick. The second special case that I would like to show you is if we have polyatomic ions, both on the reactant and product side. Keep them together as a unit or package. Similar to the first example that we did where we had polyatomic ions at OH and we kept them together. Now we're going to be looking at, in general, if we have polyatomic ions. So let's say we have NaOH, sodium hydroxide, reacting with Al2SO3 with a 3 on the outside, aluminum sulfite, producing sodium sulfite and aluminum hydroxide. One of the things that I want to point out is that here you have a polyatomic ion. SO3 is a polyatomic ion. Notice it's on the left side, the reactant side. It's also on the product side. You're not able to do this if it doesn't exist on the reactant side and the product side. So over here you have a box of SO3s. Over here you have a box of SO3s. Very important to notice, on this side there's 3 boxes of SO3s. If you were to open up the box, yes, every box contains 1 S and 3 O's, but there are 3 boxes. Over here, there's only 1 box right now. The next polyatomic ion that I'd like you to see is the OH. There's an OH here, a polyatomic ion. There's also an OH here, another polyatomic ion. So I'll use a different highlighter to highlight that, an OH here and an OH here. Once again, there is 1 box of OHs here, but there's 3 boxes of OH here. When I write out my atom inventory, I'm going to list Al, reactant side, product side, and notice I'm going to list OH. OH is not an element. It's a polyatomic ion, and we're grouping it together as a package in order to help us balance the equation a little bit easier. I'm also going to list, and I apologize, I thought I was listing Na first. In fact, I'll just erase that. It's perfectly fine to list Al first, but I really like to get into the habit of listing the elements as we see them across so that we don't miss any. So Na came first, so I'm going to list Na first. Then OH, then Al, and then SO3, the package of SO3s. So we're balancing the number of packages that we have, the number of units that we have, and if we do that, then we know the numbers inside match as well. So on this side, I've got 1 Al, I have 1 group of OHs, I have 2 Als, and I have 3 groups of SO3s. On the product side, I have 2 NAs, I have 3 OHs, I have 1 Al, and I have 1 SO3. So it's completely up to us which piece we want to balance first. So if I'm usually going to start with the polyatomic ions first. So in my mind, I want to cross out the 1 and put a 3. Well, why do I need to do that? Because I have 3 OHs on this side, only 1. So in my mind, I'm looking and I want to cross out the 1 and put a 3. So I put a 3 right here. So that allows me to cross out the 1 and put a 3. But it also changed my NAs. And now I have 3 NAs, so I need to cross this out and put a 3. But notice what that did to my NAs. I now have 3 on one side and 2 on the other. In a previous video, we talked about getting the least common multiple between a 3 and a 2, and that would be a 6. So what I'm going to do is, in my mind, I want to cross this out and put a 6. So what do I need to do right here to be able to do that? Well, I actually, because there's a 1 next to the NA, I would need to cross this out and put a 6. So now my 3 becomes a 6, but notice it also changed my OHs, so now I have 6 OHs. This also changes what I need to do here, because now I want to match this NA to a 6, so I need to put a 3 right there to be able to get to 6. I still haven't recounted my OHs on this side. I have 3 OHs on this side, but I really want to cross this out and turn it into a 6. So in order to do that, I need to put a 2 right here, because 2 multiplied by the 3 will give me 6 OHs. So there's 6 NAs on the reactant side and 6 NAs on the product side. There's 6 OHs on the reactant side. There's 6 OHs on the product side. And now notice when I put the 2 right there, I need to change the ALs, so the ALs change to 2, which is fantastic because I have 2 ALs on the other side, so it fixed itself. And on this product side also, I have 3 SO3, so I need to cross that out and put a 3, which fixed itself, which is fantastic. Keeping the polyatomic ions together as a unit or group really helps in solving the equations, because in many times they end up fixing themselves. The final example that I'd like to give you for a special case is if we have a hydrocarbon that contains an even number of carbon atoms. Use the half trick. In soccer and other sports, we have what's called a hat trick. If you get 3 goals in a game, we call it a hat trick. This is called a half trick. And I'd like to show you what that is going to look like. Let's say that we have a hydrocarbon of C4H10. It's a hydrocarbon because it contains hydrogens and carbons. C4H10, and this is a very common reaction. It's called a combustion reaction, where you take a hydrocarbon reacting it with oxygen. And the pattern is always some hydrocarbon reacting with oxygen, producing carbon dioxide and water. A very common reaction where the oxygen, carbon dioxide, and water are the same each time, and the hydrocarbon is different. When we do the atom inventory, we're going to put C, we're going to put H, we're going to put O for the atom inventory. There are 4, there are 10, and there are 2 on the reactant side. There is 1, there is 3 oxygens because there's 2 here plus 1 more, 3 oxygens, and then there are 2 hydrogens. So if we start balancing this, we know we want to cross this out and put a 4. So I put a 4 right here. I cross it out and put a 4. But I've changed my oxygens. Notice there's now 8 oxygens here plus 1 more, and that gives me 9 oxygens. Well, that stinks because I'm thinking of a number, some number times 2 to give me 9. And there is no whole number times 2, so I can cross this out and put 9. But there is a half number, and half of 9 is 4.5. So if I put 4.5 in here temporarily, this 4.5 times 2 gives me 9. And I apologize. What I should have done is fixed the hydrogens first. So I'm just going to back up for a second and get the hydrogens fixed first. And the reason I want to fix the hydrogens is that's an easy fix. Some number times 2 gives me 10. I want to cross this out and put a 10. So I put a 5 right here. And when I put a 5 right here, that gives me 10. And now the hydrogens are balanced. And now I recount the oxygens. 8 oxygens plus 5 more give me 13. So once again, I'm at a half number, but the reason, and it's important I made that mistake, the reason I wanted to do this is notice the carbons are fixed, the hydrogens are fixed, and now all I have left are the oxygens. Previously, when I was going through this, I hadn't fixed the hydrogens yet, so I don't want to use the half trick until the other elements are balanced. So now I can use a half trick. Well, what's the half trick? Well, half of 13 is 6.5. So I temporarily put 6.5 in there because now the 2 becomes a 13 and everything is balanced. I had fixed everything previously. I put the half in there on the 2 and everything is balanced. But there's a rule for balancing equations. You are not allowed to use halves. You only are allowed to use whole numbers. So now I need to turn this into a whole number. So how do I do that? I take the entire equation and I double all the numbers. So this invisible 1, and I'll go ahead and put it here, this invisible 1 turns into a 2. The invisible, or not invisible, the 6.5 turns into a 13. The 4 turns into an 8, and the 5 turns into a 10. So my coefficients to balance this equation would be 2, 13, 8, and 10. And what we've done is we used the half trick. This comes up anytime you are dealing with a hydrocarbon that has an even number of carbons. And when you have an even number of carbons, you save the oxygens for last and use a half temporarily and then go back and double all of the coefficients. I hope this helps with the 3 special cases of balancing chemical equations.